Hello, everyone. The title of our paper is Spatially Compact Dense Block Mining in Spatial Tensors. First, we need to understand what is a dense block. A dense block can also be referred to as a dense subtensor. Through the communication between Bertie and Gary in the diagram, we can identify key information and extract their purchase records. Similarly, we can represent the purchase records of other individuals in a tensor structure. The orange and blue blocks in the diagram can be referred to as dense subtensors. A dense subtensor refers to a subset of data within a large tensor where the attribute value set formed by various attribute dimensions is as small as possible, meaning that the number of attribute values is minimized. From the perspective of density, the orange tensor is clearly superior to the blue tensor. However, if your goal is to mine users who live nearby and exhibit similar purchasing behaviors, in order to target them with complement ads for that region, you will notice that the data distribution of the orange tensor spans the entire country, while the blue tensor's coverage is limited to a city or even a district in some cases. Considering cost, you would definitely prefer a dense subtensor with a spatial distribution limited to a city or a district. So, how can we make the algorithm aware of this? We propose a new metric and apply it in our algorithm, which not only considers the density but also takes into account the spatial coverage of the subtensor. In the new scoring function, the larger the spatial coverage, the lower the score. Finally, we calculate the scores of the two subtensors using the new scoring function. Through the new scoring function, it is clear that the score of the blue subtensor is higher than that of the orange subtensor. We use a filtering and refinement framework to mine spatially compact, dense subtensors. The filtering phase uses the method described below to process the spatial attributes of the tensor, and the refinement phase uses the existing dense subtensor mining algorithm to process the traditional attributes, ultimately outputting subtensors with high density and low spatial coverage characteristics. Now that we know spatially compact dense subtensors are those with high density and low spatial coverage, how do we mine subtensors with these two characteristics from a tensor? The first method is to continuously reduce the spatial coverage of the tensor through partitioning operations based on the scoring function. By repeatedly partitioning the tensor, we can eventually find high-density, low spatial coverage subtensor, as shown by the green tensor in the figure. The second method is to first divide the tensor data into smaller cells based on its spatial attributes, and then use an expansion operation to find high-density and low spatial coverage subtensors. We will expand from a single cell according to specific rules, until no further expansion can improve the subtensor score.